So good afternoon and good morning, everyone. Welcome to today's webinar, Foundational Statistics for Forensic Toxicology. This is session 5, a calculation of type A data from control data for measurement uncertainty. Our presenters today are Sue Paring, Quality Manager at the San Francisco Office of the Chief Medical Examiner, and Aria McCall, Technical Lead at the Tarrant County Medical Examiner's Office. Without further delay, I'll go ahead and turn the session over to our presenters. Thank you.
Well, welcome back, everyone. Let me pull up my screen here and we'll get started. With a long title like that, I think it's worth mentioning that this is session 5. Thanks for returning, and we're going to pick up this conversation from some of the things that we've talked about previously and to fold it all together. Let's start by just a quick reminder about this session's detailed learning objectives. Previously, we had discussed control charts and its various elements, right? And in this session, we're going to apply the statistics we've covered thus far into the usage of control data in measurement uncertainty. This is not like an A to Z of how to calculate measurement uncertainty, but we want to consider how statistics are used in this process and to really solidify the understanding of the concepts that we've laid out thus far. We also want to highlight a few of the potential missteps to avoid on this topic. Many folks find measurement uncertainty daunting, and our hope is that you leave today finding it less daunting and that this significant part of measurement uncertainty of inclusion of type A data will be addressed and hopefully a bit demystified. So let's start with what's in the title of this session, right? Calculation of type A data. What is type A data? Type A and its counterpart, type B data, are terms used to describe the types of data that comprise the components that make up a measurement uncertainty. Type A data is the kind of data collected through independent and repeat observations. Right, so multiple observations, multiple measurements, multiple data points collected over whatever duration of time. And we want to be sure that there are enough of these, or that there's a significant enough of these collected. Otherwise, we're going to use a t-distribution to appropriately summarize or characterize them. To contrast this with the other kind of data for measurement uncertainty of type B data, type B data is the kind of data known through some sort of tolerance or some sort of set limit, right? So rather than collecting observations, this is a preset, predetermined range of values where something might take place. This commonly takes place in the form of the tolerance for a calibration specification of the equipment, such as a volumetric pipette that we might use in the measurement process in forensic toxicology work. Now, these generally exist in a rectangular distribution, as a dispersion of data within this tolerance or limit is unknown and can range, right? It's not an actual distribution of values that were collected. It's actually just that the tolerance can be what it can be, right? From a minimum to a maximum range, and that forms a rectangular distribution. It is possible, however, if sufficient information is known or that this tolerance is applied a different way, that you may be able to justify a triangular or trapezoidal distribution. And if this information looks a little familiar, we did touch on this briefly in session 2. We were kind of queuing you up for this. Now, depending right on the type of data, the distribution, and the subsequent summarizing of them for inclusion in measurement uncertainty calculations differ. Right, you saw this slide in session 2, the left being normal or t-distribution, and the right being rectangular, trapezoid, and triangular distribution. While these represent all the various, well, not all of them, but many of the various kinds of distributions that may exist, our normal and t-distribution are commonly reflected in that type A data, whereas the rectangular is more associated with our type B data. Remember that distributions as a whole is a statistical concept, whereas type A and type B data are specific to measurement uncertainty and the kinds of components that are related to this. So alas, let's focus on type A for today. Type A, right, there's independent repeat observations that it follows some sort of a normal distribution or a T distribution, and type B being the tolerance ones, we're going to set that one aside. If your brain is also recalling this slide from session 3 and associating type 1 and type 2 errors in your brain, let's sever that connection now. These two things have nothing to do with each other. Type A and type B are ways to describe data that influence measurement uncertainty, whereas type 1 and type 2 errors are associated with statistical tests and hypothesis testing that is not the same thing, right? They're not at all the same thing, even though there's a pair of these and a pair of those, right? So just because there's two clusters, type 1 and type 2 errors, type A and type B data, they're both called types, there's absolutely no association, right? And I'm just going to leave that there, right? Just because there's two types doesn't mean they're the same. So type A data contributes to our calculation of measurement uncertainty. And how and where in the process of calculating measurement uncertainty does that fit in? And what guidance does there exist on this? Now, the topic of measurement uncertainty is not unique to forensic toxicology, nor is it new to the greater field of analytical chemistry either. And many resources on this topic exist, right? So for a pure methodological understanding, not specific to forensics or forensic talks, the go-to document is a document titled Evaluation of Measurement Data, Guide to the Expression of Uncertainty in Measurement, or GUM for short. The document describes in great detail the evaluation of measurement uncertainty, and the appendices are rich with explanations of statistical concepts and examples of MU for different types of measurements. Many of them seem quite foreign to us as analytical chemists, but it's a kind of a pure methodological perspective on this topic. And section 8 of that document summarizes what's now commonly known as the GUM 8-step process of evaluating measurement uncertainty, and this is where we'll start today. Now, first in that process is to specify the measurement process. What are we testing for? How is it being tested? What's the process look like, right? What's a sample prep? What kind of equipment is being used? What kind of instrumentation is being used? How do the components actually come together to make this measurement complete? The second is to identify the components that contribute to uncertainty, and then to quantify those that do contribute, convert them into standard uncertainties, combine them, calculate the expanded. And number 7, evaluate the expanded uncertainty. This is probably the one that has the least amount to do with math and the most amount to do with the rest of your laboratory, your QA system, the fitness for purpose of the method, your stakeholders, what you're actually testing for, how these results are used. And lastly, in step 8, reporting the expanded uncertainty, right? Like I said, we're not going to go through each of these in detail here, but I do want to highlight that QC data comes in here in step 2, identifying the uncertainty components. Typically, the largest measurement uncertainty component, we have the reproducibility of the method. And reproducibility is described through the collection of repeat observations, mostly independent repeat observations, right? Does that sound familiar? That's indeed how type A data is described. And reproducibility is a form of type A data in the evaluation of measurement uncertainty. This is collected through those repeat observations and evaluated by statistical methods. So let's pick up with some actual data, some actual QC data similar to what we saw in session 4. And for this example, we're going to use an ethanol method or a volatiles method where ethanol is being tested for. And in this method, there's a 0.10 gram per cent QC that's being run. And we collect all this data. You can't see the numbers. You don't really need to see them. They're near 0.1, right? We collect data point after data point. And we've even set up a nice Levi Jennings plot that visualizes all the points. Easy to see if there's any trends, but also which points are more than 2 or 3 standard deviations from the mean. In other words, if the z-score is easily plotted here for visualization. So now what? We have all this data. We know this contributes to reproducibility. How do we summarize this for inclusion in calculation for measurement uncertainty? The GUM leads us after step 2 to step 3, quantifying the components, and the GUM describes this in much detail, right? That this is done by calculating the relative standard deviation of QC samples, right? These many independent repeat observations need to be summarized, and it's done by calculating the relative standard deviation. Now, recall from session 2 that relative standard deviation is also known as CV, right? And also CV, as we defined and covered in session 2, is simply the standard deviation divided by the mean represented as a percentage. So taking a small step back, first the standard deviation. This is obtained by taking the square root of a variance, right? But for QC samples, because we're estimating the method performance, this is a sample and not a population, right? So lowercase s instead of the Greek letter sigma, and lowercase n instead of that capital N for population, right? So we're calculating s for standard deviation of a sample, not sigma. While they're very similar, right, what we're dealing with is typically going to be a standard deviation of a sample or an estimate. So we take all these values and we calculate the standard deviation by calculating the mean of all these data points, the difference between each individual data point and the mean. We square them, sum them all up, divide this by n minus 1, and take the square root of it all. Right, and of course we can do this by pen and paper since you now understand the calculation itself, or you use a calculator because you want to pull up your TI-82 to play some Tetris, or some other computing software statistical package because you have better things to do, right? But however you come to this, we know we're half of the way there. We've calculated our standard deviation from all those QCs that we've collected. And in this example, it comes out to 0.002478, right? So what's next? We're not done. We don't need just the standard deviation. We need what? The relative standard deviation, or the CV, right? So again, from session 2, the CV is just that standard deviation divided by the mean represented as a percentage. And that percentage can be done just by multiplying by 100. I don't love this formula because I think it's a little misleading. You're not really multiplying by 100. You're actually just showing that decimal as a percentage. But nonetheless, you get the same thing. You get the idea here. And so that standard deviation, which is in the units of the thing that we're talking about, right? The variance is that unusable squared unit that is meaningless. And you divide it by the mean of all those QCs. In this case, it was 0.101 grams per cent, right? So you divide these two and represent it as a percentage. And what we get is the CV, or the relative standard deviation. In this case, it's 2.5%. So in words, this means that relative to its mean, right, the dispersion varies 2.5%. If I told you that you were going to the store and they were running this massive sale and it was 2.5% off, you'd say big whoop, right? Not a big deal. And this usefulness of a CV is that it's relatable, right? As a percentage of what you're measuring, how different do these values vary? And 2.5% seems pretty reasonable. Of course, depending on what you're talking about. A sale for, I don't know, your next computer versus 2.5% off in a measurement result that's going to court, right? Depending on its application, you might respond a little differently to it, but it gives you an idea of what kind of variation we're talking about. So to land this particular example, this brief and really quick example, we're going to take a little creative liberty and shortcut to the end of this 8-step process. So we identified the uncertainty component of this type A QC data, right? We quantified it and turned it into a relative standard deviation to include it. And we're going to just say, hey, we know, right? You saw from that table, there's way more than 30 data points. So we're going to assume that it's sufficiently normal with an expansion factor of 2 at 95.45% confidence. We're going to ignore all of the contributors, pretend that there's nothing else affecting the measurement uncertainty. And when we shortcut this, what do we get? You get 2.5, right, times 2 for that expansion factor at a 95% confidence. You get an expanded measurement uncertainty of 5%. So if you had a measurement result from the same method, right, not a QC, but an actual test of an unknown sample producing a value of 0.11 gram percent, you have an expanded MU of 5%. What does that mean? Do not let the units here confuse you. Gram percent, 5% MU, right? Gram percent is just the units. You could even think of them as nanograms per mil or some other unit. It really doesn't matter, right? The 5% is relative to that value. So the expanded measurement uncertainty of that is 5% of 0.11, which gives you a result of 0.006 gram percent. So if you express this as a result, what you get is that test measurement result, 0.11 plus or minus 0.006. If you express this as a range, it's going to be 0.104 to 0.116 with a 95% confidence. So I just want to say this is a very, very simplified example, right? This example versus reality, there's a big, big difference, just like saying a sprinter just does that thousands of times over to become a marathon runner. And you can tell by the physique difference in those how different this example is from reality, right? We've shortcutted a lot of things, but just to show the type A component and how it contributes to the measurement uncertainty. So in addition to the GUM-8 stuff, it's worth mentioning that another resource is available that is specific to forensic toxicology in the form of ASB 056, the standard for the evaluation of measurement uncertainty in forensic toxicology. Now, at the time of this live webinar on July 11th, 2024, this is not yet published as a national standard. It is anticipated, but it is out for recirculation. This is following initial revisions after some other public comment period. And at this time, comments can still be submitted on this recirculation. Only comments are accepted based on revisions previously made, right? So no new comments, but nonetheless, tune into this conversation, take a look at what comments have been made for you previously and what revisions have been made in light of that. This comment period ends in a couple of weeks on August 19th. And in this standard, the focus is specifically on forensic tox. So unlike the GUM, where it's kind of a pure metrological, broader perspective, this is now just forensic tox. And the appendices have some very relatable examples and delves into this concept of MU that we're going to be a bit limited in our discussion of today. So another resource for you, right? And within that document and that standard, ASB 056 comments on type A data. It's data, this QC data, this type A data, whatever your reproducibility measurement is, must be representative of your measurand, of what you're measuring, right? Is it ethanol, what it is it fentanyl, is it whatever? And it must be representative of the range and of the matrix, the range of values, whatever that analytical range is for your test method, and the matrix, blood, serum, urine, you name it, right? And lastly, that it must be representative of ongoing work. And so ASB expands on this to say, well, where does type A come from? The one we just talked about was reproducibility in the form of QC data. But specifically, ASB 056 outlines three. Validation data is a viable source of type A data, right? Repeat independent observations. However, they're limited in quantity and typically limited in duration, right? And so initially, this is okay to use. Then there's quality control data, which is collected over time and is going to be a much better representation of ongoing performance. And so once you've moved past validation and collected some ongoing QC data, this is the preferred type of type A data to include. And lastly, there's a provision for proficiency test data to be used as type A, right? Also independent repeat observations. But this is only acceptable if it is a traceable PT and the consensus value is not considered the traceable true value of a PT, right? So these are all repeat observations characterized or can be characterized through statistical evaluation, but each has its unique attributes and its appropriate application as well. And to make this point a little more clear, I'm going to walk you through the example of comparing validation and ongoing data in this way. What do I mean by that? We're saying that the data for um, type A inclusion and measurement uncertainty must be representative of ongoing work, right? And is validation representative of ongoing work? ASB already talks about this, but we're going to use some of these statistical concepts we learned about in earlier sessions to really drive this point home and to get a little practice using these skills that you've acquired. Now, in the validation, sorry, the spacing of this didn't turn out great. The validation data set produced 39 samples or 39 replicates, whereas let's say in the first year or the first half of the year, we acquired 173 data points, right? So you can see validation kind of limited. It's just the beginning of the method, whereas as the first year goes on of this method being in production, many more data points are available. And from that validation data set, we've got a mean of 0.100985. A standard deviation is shown there, and a CV, or a relative standard deviation, of 3.2%. Let's contrast that with the year one QC with 173 data points. The mean is there quite similar. The standard deviation looks narrower, and the CV is about 2.5%. So you're asking, hopefully you're asking, are they similar and are they similar enough, right? It needs to be, the data that we include needs to be representative of ongoing work. If we were to use validation, is it representative of ongoing work? ASB allows you to use validation initially anyway, so this question is kind of moot, but for the sake of this example, just hang in there with me. By looking at these numbers alone, right, the means, the standard deviations, and the CVs, are they similar? Are they similar enough? How can we discern or find an answer to this question? Are they similar enough? So flashback to session 3 in Brigitte's presentation, she covered the F test, right, that assumes normality and independence, and testing for differences in variances with a squared standard deviation, right? And are these different enough? This is a test that we can use to discern that. And so I'm going to refer to our handy dandy Excel data analysis tool pack. Brigitte spent some time talking a little bit about introducing R and other statistical packages that are available, but Excel is something that we all have, likely have in our laboratories and have access to. So if you've never done this before, a quick Google search of Excel data analysis tool pack will show you how to add it and how to access it. There's lots and lots of information about this online, so we won't spend much time on it now. The screens might look a little different depending on which version of Excel you're using, but nonetheless, you can see all the data analysis options that are available to us built into Excel. This is not something you have to install separately or pay for separately. It's just built in on the default installation, right? And within here, we have an F test sample for two sample tests for variances that's available. And you just put in where your data is for your first variable, your second variable, where you want the results to be put in, right? And of note, be sure when you're using this, if you're trying to do an F test, right, of two sample sets, that the variance of variable 1 is higher than the variance of variable 2. And I'll explain why in a moment, but just keep that in mind when you're using it. Don't just pick whichever one is 1 and whichever one is 2. Pick the one that has higher variable. And you'll see that in many of the online tutorials of how to use an F-test, how to access an F-test in Excel. The output of this little tool pack gives you something that looks like this. You have the validation in the year 1 data that I selected shown up here with those means that we saw earlier. And what's displayed here are the variances rather than the standard deviation, but nonetheless, you get the same idea here. The number of observations, the degrees of freedom, and so on and so forth. And the value of interest that we want to highlight is this one-tail p-value, right? If we're comparing a p-value to a critical statistical significance threshold of 0.05, this is the p-value that we're comparing to that. But I want to mention that this is a one-tail p-value, right? And what does that mean? If you recall from session 3, one-tail versus two-tail is talking about what kind of difference are we expecting. One tail is either that there's a positive or a negative decrease versus a two tail is just saying that like they're just not the same. We'll go over this in a couple of different ways, so hang tight if this is not clicking for you yet. The point I want to highlight though is that in Excel, it is exclusively assessing for this negative decrease of a one tail comparison. And that's why the warnings exist about putting in the higher variance first and then the lower variance to see if it indeed is decreasing. If the variance of your data set, the first data set, is greater than the variance of your second data set. Now, this, you might think, why has Excel led me awry? All I want to know is, are they different or not? How do you convert this one tail into a two tail? And so again, that one tail, remember, is that variance of one is less than or equal to the variance of the other, or the alternative hypothesis is the other way around, right? And you're going to make that comparison. And that 0.00985 p-value, right, is it less than 0.05? Now, what we're actually interested in is a two-tail test, right? It's not just one situation where one is greater than the other. We're interested in, are they different? I don't really care which one is greater, just are they different or not? And that 0.05 or that 95% confidence needs to account for both possibilities, right? One greater than the other or the other greater than the other. A greater than B greater than one, greater than A, right? So the actual hypotheses that we're working with is not that one is greater than or equal to the other. It's that they are equal. The null hypothesis is that the variances or the differences, the dispersion, are equal versus its alternative hypothesis that they're not equal, right? Not that one is greater than the other, just that they're simply not equal. So how do you convert this into a two-tail? Well, it's actually quite simple. If the one-tail p-value is 0.00985, you just multiply it by 2. You take one tail, you multiply it by 2, you get two tails. So the two-tail p-value is 0.018. And in Excel, you have this limitation that it only gives you a one-tail p-value, right? And so that's all we have. You take that, you multiply by 2, now you've converted it into a two-tail. So what does this two-tail p-value tell us? 0.018 is less than 0.05. And so do we accept or reject the null hypothesis? Your p-value is less than 0.05. We're going to reject the null hypothesis in favor of the alternative hypothesis, which says that the variances of validation in year one are not equal. So circling back, the question we were answering was, is validation data representative of ongoing work? Are the variances equal? Are they similarly representative? And what we've answered in this data set is that indeed no, right? And like I said at the beginning, validation data is only appropriate to use as a source of type A data for measurement uncertainty initially, right? Due to that limited quantity, limited duration, ASB just simplifies it. You don't even need to do that test we just walked through. It's just that, hey, it's okay initially, but once you have more data, you should use more data, right? And that example showed just how different those are. Statistical significance at a 0.05 alpha. Another common question related to measurement uncertainty and control data is that, can one measurement uncertainty be applied to a range of results? And if this sounds familiar, this is that second dot point we talked about earlier, that the data you include must be representative of the range, right? We're not talking about matrix right now, just of the range of tests. So an example to drive this guy home, if in a test method, let's talk about that same test method, we have two QCs, one at 0.08 and one at 0.15. And these are different parts of the range of values within this same test method. So are they similar enough? Well, if we look at the QC data for these two levels of QCs, you can see that the counts are the same. They're both run in every single batch, so we end up with the same amount of data, and that the means are reflecting how similar they are to the target concentrations. We're not really comparing the count or the mean of these values. What we're interested in is if that standard deviation or the variance, right, are represented or not. And looking at these numbers, it's very hard to tell, is this significantly different or not? And again, we're asking ourselves the question, are they similar? Are they similar enough? So just as in the previous example, what we're going to use is that F-test again. And so we're just going to walk through once more what this F-test does for us, right? So one data set is at 0.08, the other data set is the 0.15. The mean and the variances appear here. And that p-value is here on the second to last line, 0.0339 approximately. So that one tail p-value, right? And remember, to change that into a two tail, what do? We simply multiply that by 2 to make that comparison. So I'm going to skip through these because this is quite similar, right? One tail is associated with a particular null hypothesis, whereas what we're actually interested in is whether or not the variances are equal or not. So taking that original one tail p-value, multiplying it by 2, we get a 0.068 approximately. Now you can see quite easily that this is greater than 0.05 alpha. And so we, in this situation, we fail to reject the null hypothesis. I always thought it was funny, that we say fail to reject the null. It's like the double negative is really not necessary, but it is the the specific accuracy of that statement is quite narrow because that is what you're doing. You're not saying that I accept the null hypothesis. We're just failing to reject it because that's the purpose of the test. It would kind of mean the same thing, but there are slight nuances to the meanings of those words. And so we fail to reject the null hypothesis, and we can say that there's no evidence the variances are not equal to one another. And so answering the question of is the 0.08 and the 0.15 QC data representative of the range, are they similar enough? Here we've answered that yes, they're okay. They are similarly representative. So if you include one, just the 0.08 QC data or the 0.15 data, actually they're similar enough that it can be representative of the analytical range. Now, it might be worth noting that you might have an even lower QC, maybe a 0.03 or something, that might be relevant to also compare to make sure it's representative even down there, right? But this type of testing is the tool we can use to answer these questions. Are they representative of the range if you have multiple QCs throughout your range or of ongoing work? And one more kind of call back to an earlier concept. You saw in the F-test that what we're interested that the F-test assumes that the data sets that we're dealing with are normally distributed and that they're independent. Independence you can kind of assess by understanding, from QC to QC, are they is the result of one going to the effect of the other? But this question of normal distribution comes up a lot. As Brigitte mentioned, it is a foundation and often an assumption made that needs to be made and met to use responsibly the statistical tests that we're talking about. You may recall, I think in session 2, that I said, well, if you're asking yourself, how do I know if it's normally distributed? Sometimes we just say, how do we know if it's not normally distributed? And visually do so, right? But that visual reliance is not so, well, it doesn't feel so quantitative or scientific. And Bridget had also brought up I'm not even going to try to say it, the KS test for normality, right? In this specific test, she presented 2 examples, but this particular one we can dive into as well to show how a normality test might be used. And I'll confess this to you now, which is I am not familiar with this test. And I thought this is a great example for us to walk it through to say that if you come across a test that you need, what do? You can search it up. I quickly found one from statology.org that I found pretty easy to digest after hearing Brigitte's introduction to it, but also read about it and then check it. Look at a couple of different ones that you might find to find out, okay, does this sound right? Are they talking about the same thing? And you might find that one explains it a way that's better, easier for you to digest than another. I also want to mention that R or other packages do simplify this, but does your brain actually get it? And I'll say I could easily plug something into R and it makes the calculation really easy, but I think I'm missing out, at least initially, the first couple times I'm doing it. Do I actually understand what's being done? It does it quite simply. It's almost too easy, right? And it is critical that we understand the limitations and the specific conclusions that we're actually drawing, that we don't misattribute some sort of conclusion that the test is actually not suggesting. So for this KS formality test, right, the null hypothesis is simply that the data is normally distributed. The alternate hypothesis is that it's not normally distributed. And Excel can help us do this too. It's not as simple as the data analysis tool pack, but using that resource that I mentioned earlier, it gives you some step-by-step instructions. First is to organize your data set sorted low to high, so in increasing values. And the questions that the KS test does is to ask, well, in producing the test, actually, the questions it answers is if it was perfectly normal, what is the expected value of each data point, right? Of all these data points that we're dealing with. If it was normal, what would each of them be? And that's why the sorting of low to high is so important. And how different is each value versus the expected normal value? And this can be summarized with a KS table to compare with a KS table's critical value, or you can calculate a p-value. So the specific resource that I shared earlier walks through this. That was on statology.org. If you Google it, it's one of the top ones that come up. And there are other resources like this too, but it breaks it down into all the things that we need to be able to answer this question. That resource gives the formulas for all the calculations and a sample data set if you want to play with it to make sure that you understand the concepts and that you're using the tool correctly to make that calculation. And then you can replicate this for your own data. And that's what we're going to walk through a little bit today. Now, I really like this way of digesting this information because it forces you to see the individual components. It forces you to look at each of the individual calculations to better understand how this all fits together to answer the questions this statistical test presents to us. And so from that sample data set, we can then apply kind of the formulas and the things that we've learned to our own data set, right? So we have our null and alternate hypothesis, and where the max value, that calculated formula of the max value, is greater than the KS critical value, we're going to reject the null hypothesis, right? And if it's the other way, we fail to reject. And if we can reject the null hypothesis, we're basically saying that the data is not normal. So with the data set that we're talking about, I took those 305 QCs that we used in our first example of a 0.1 QC, and we sorted it in this low to high here. And if you've never done this in Excel, maybe you've come across it accidentally. If you hit Control tilde, that little symbol to the left of the number 1 on your keyboard, Control tilde shows all the formulas, and you can make sure that the formulas were entered as that tutorial had asked for. If you hit it again, it just shows the actual numbers and the calculated values, right? And so column by column, you put in these formulas, you have your entire data set, you expand these down or fill them down to cover all 305 rows of data. You can take a peek at the mean and the standard deviation, right? What we saw earlier in that data set. And this max value is highlighting the max, right, of G2 to G306, which is in this column, the max difference. And that's that critical value we're talking about for this KS test. And zooming in on that, that max value is 0.03, 0.037 approximately. So we have a KS table, looks very familiar to our T distribution or our student T table. And we're looking for an alpha of 0.05 for significance. And your N, right, the number of data points here is over 50, right? We had 300 plus data points. And so that critical value is where those, right, that row and that column intersect. And the critical value here is 1.358. And what does that mean? Where does that leave us? Right, this KS test, we had a max value of 0.0368, and the critical value is 1.358. It's less than that. And so we fail to reject that null hypothesis, and we can say that the data is normally distributed. Right, the max is less than that at an N of 305, and we've answered the question of, hey, is this data set normally distributed? Can we then follow on using an F test or something else to answer that question? And in this case, yep, it is normally distributed, and so we can move on. So before we wrap up today, there's a couple of common missteps I want to highlight. And this is something I hear about, I get questions about, and I've seen happen time and time again. When we have these tools available to us, whether it's an R or an Excel or whatever package you choose to use, and we're applying these statistical concepts, we do not want to blindly apply k equals 2, okay? Specifically to measurement uncertainty, where you might have a small sample size. This method is not being run many times. Your n might be something low like 15. You're going to want to consider the appropriate expansion factor, not just the default k equals 2 to reach a 95.45% confidence, right? And you got to ask yourself, is it normal? If it is normal and your n is really large, sure, k equals 2 is okay. But when it's really low, consider what happens, right? The degrees of freedom are quite small, right? And Aria had mentioned this in session 1, but when you have such a small sample size, it has an impact on what we're talking about here. And you can see this in the student T table lookup. If you have a small sample size of about 15, and you're looking for a 95.45 confidence, the actual expansion factor, when you have a 14 degrees of freedom, right, that 15 minus 1 is 14, you actually have something of about 2.195. That's 2.2-ish, right? And that is a pretty big difference from your K of 2, right? Do not blindly apply K of 2. And be aware that if you have a small sample size, you might be underestimating your measurement uncertainty by using the wrong expansion factor, right? And secondly, do not blindly assess a p-value of less than 0.05. It's really nice that it's easy to calculate a p-value, and we have tools that quickly calculate that for us. But don't blindly assess that, right? You might have been so preoccupied of whether or not you could that you didn't really stop to think if you should. And specifically, I want to warn you to consider which test that you're using, and based on that, what your hypotheses actually are. What is the null hypothesis? What is the alternative hypothesis? What is it actually telling you? And how do you use what the conclusion actually says? Does it answer the question that you're talking about? Another common question is, when can I exclude data? And I'm going to call back on two previous slides here from other sessions, that while we have statistical tests for outliers, it's actually a bit more specific when we're talking about control data, right? And Aria had mentioned this. The ASB 054 addresses that, they should be recorded, including those that fail. Even if it's a statistical outlier, control results should be included in that data. The ones that are valid to exclude are the ones where we have known issue, drop QC, that it's a known mistake during extraction, and so on and so forth. So I want to leave you with this. Another question that often comes up, and I hope that you now can answer this question for yourself, of how many points do I need to calculate the MU properly? I think maybe the question is not so much how many points do you need to calculate the MU properly, but given how many points you have, how do I calculate it properly? There's no magic number for this. However, knowing what you know now, hopefully you can answer that question a bit for yourself. Again, our goal for this series was really to move you from one of these quadrants to the next, right? Of unconscious incompetence to conscious incompetence. And now you've hopefully learned a bit more so that you can move from one quadrant to the next. You might be asking more questions for a period of time until you start answering those questions for yourself, but hopefully you're moving in that right direction. So to wrap this all up, I want to say statistics is not a topic that you can watch a 5-minute YouTube tutorial on and become an expert in. And like I've said before, I still don't feel like I'm an expert by any stretch. However, if you stack 50 of these over the next year, or 500 of them over the next 10 years, as you continue your journey to learn to love statistics, or at least not hate it, I do expect that you'll make some significant progress. You've heard me say it before, and you'll hear me say it again before we're done with session 6, but there's no better time than now to take or retake statistics. If you've never taken it before, there are college-level statistic courses available online. It couldn't be easier. And there's actually those that are online that are also self-paced, and even those that are online, self-paced, and free. I mean, there really is no excuse not to take or retake a statistics course. If you've taken it before, take another one. Sometimes another voice, another format, or another perspective instruction strikes a chord where the concepts just weren't clicking before. Just as some of you may have found that I explained it in a way that made more sense to you or less sense to you. Trying another voice, another presenter, another instructor, you may find more success the second time you hear it. And not only that, but now having seen the application of statistics in the professional work that you do, it'll be easier than ever to engage with the concepts in a course, even if it's not specific to forensic talks. Having a place in your brain to file the information away, knowing just how you'll use it in your professional day-to-day life, may be just what you need to level up on your statistical knowledge. So keep the questions coming, as our next session is our fireside chat and the conclusion of this webinar series. Don't miss it. Don't skip out on it just because there's no, lecture format. I think it'll actually be the most interesting, I hope, for all of you. We'll discuss with our various presenters those nagging questions where Wikipedia or Google gives you circular answers for, or where ChatGPT tries really hard but can't seem to understand just what you're asking, to close out our 6-session webinar on foundational statistics for forensic toxicology.
Great. Thank you, Sue Piran, for the presentation on our session 5 today. If you have any questions, put it in the Q&A. We still have about 10 minutes that both Sue and Aria can answer some of your questions. We did have a little bit of chat. Somebody asked a question, just looking at some of your resources you're using to calculate the stats. And I think most of you are populating in Excel or some maybe R. And then we have one question about some of the resources that you've been talking about, Sue, that are free, about providing links to those.
Yeah, the actual resources for that, I think we'll address at the next session, and they'll be, I think, Catherine, correct me if I'm wrong, if they're already on the website for the webinar series. There are many, many available ones. A personal favorite of mine that I've been using for many years is Khan Academy. And the lectures are short and it's very, very accessible language. And the huge benefit of YouTube or these like online self-paced presentations is that you can pause it, rewind it, listen to it again, right? If you space out for a second, you can just go back, listen to it again. If you need to hear it one more time, you can watch that same section again and again. And the same goes for sources to learn R, Kim, to answer your question. R, Excel, I mean, there are so many resources. Some of my favorites, I think you'll see on the website, is for Excel is Mr. Excel and Excel Jet are some of the go-to ones for me. I've played with R and I really like the tool of it, but I find a much harder time retaining what I'm doing in R because I'm not so familiar with it. And so that's why I choose to stay in Excel for a lot of these things, because it forces me to really process each of the steps, the things that I'm dealing with. But we'll note that question for good resources for R, and I'm sure Brigitte could share some as well if she hasn't already in the chat. We'll be sure to provide some of those as well.
All right. Thank you, Sue. And you're correct. There will be links to some of the resources that our presenters have spoken about in the presentation. So that'll be on our FTCW website. So if there, let's see.
I have a quick question for you, Sue, about normal distribution. We've had a lot of talk about distributions and the way they can look and the different types of distributions. And ideally, when we're doing validations and testing and stuff, we like to see a nice normal distribution. But is it wrong or incorrect to continue on with an assay that doesn't display normal distribution?
Yeah, that's a great question. I think the interest in it being normal is so that your subsequent actions make sense, right? If you have actually a t distribution and you're applying an expansion factor of 2, like in my example where your n is 15 and the shape of it is quite different, it can underestimate, or in other circumstances or other applications, you might be overestimating, right? It's like not that precise or it's not that accurate. You think about, especially for measurement uncertainty, how interesting this is. You do all this work to be as precise as possible. And then because of a statistical misstep, you then introduce a 10% underestimation of that, right? And like, what is the point? So I think the concern is really how you are using that data, and what the subsequent calculations have to consider based on that distribution. Nowhere does it say that your data has to be normally distributed, right?
Right.
And you also want to keep in mind, depending on how number handling in your laboratory works, right? If it's rounded, if it's truncated, you might see a certain lean one way or another based on that. Or depending on, how many decimal places or how descriptive you are in your data, that, I'd say normality is not like, it's not a hard and fast requirement. It's much more about how you use that subsequent data and are you considering.
Right. So would it be safe to say that most of the examples and demonstrations that we see in some of our guidance documents are making kind of a presumption of this normal distribution, and that if you didn't have normal distribution, it would require a more intimate relationship to know if you are calculating these types of limits and tolerances correctly?
Absolutely. Yep, exactly. And it is worth mentioning too, I think in many of our labs, when you're collecting hundreds of data points a year, I mean, the central limit theorem, right? We talked about that, I think, in session 1, is that data tends to be, if it is normal, if it's randomly distributed, it's going to end up being normal if it's a solid and reproducible measurement process.
Right. Thank you.
Okay, we do have one in the Q&A. It's about they understand including drop vials and no mistakes from their mu calculations, but including those that are outside acceptable criteria, but for unknown reasons, those are not used to justify and report specimen results. And because of that, they have no impact on subject results. And that's why they remove it from their mu calculations. And they are interested in thoughts on that.
Yeah, I think this is exactly what ARIO is trying to address, right? Just because it's out doesn't mean that we exclude them. And it's actually of interest to keep those data points in because it's happening for some unknown reason, which means it could happen again and you have no real idea of why that might be. And that can happen just the same for your measurement of the unknown, right? And so that kind of variability is kind of expected. Outliers, do exist. Excuse me. And even at like a 99% confidence, like 3 standard deviations away, that's 99%. It's still not 100%, right? But it is part of that distribution and it's part of that consideration of your, to be representative of the measurement process. So in short, I would keep them in. Just because you don't know why it's out and just because it is out does not give you sufficient cause to just drop them, to exclude them from measurement uncertainty. If the concern is that that outlier is having a significant impact on your measurement uncertainty, maybe you take a look at how many data points are we talking about. If you have 15 and one of those is an outlier, it's going to sway that mean and that standard deviation pretty significantly, right? But imagine if you have 300 data points and you have that one outlier, it's going to have much less of an impact and much less of a sway on those values and its contribution to measurement uncertainty. And I think that's really the point of interest here.
Great. Well, thank you, Sue, for presenting today and answering all of our questions that came up. And thank you to all the guests who have come to session 5. And we hope to see you back on Thursday, July 18th for the final session, where you'll sit down with all of our presenters, Sue, Aria, Brigitte, from all the sessions, as well as a statistician from RTI will be there as well. So have a good rest of your week.
Thanks, everyone.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.